Hello everybody and welcome to my second tutorial about Freecad CFD-OF. In this topic, I will show you how to build up a simulation of a tube diameter shift. In the drawing, you see the model. First, what we will do is calculate the speeds and the pressures with an analytical model. We can say that the incoming speed is 10 meter per second. So that means that in the second tube, the speed will be 0.4 meter per second. Next, we will calculate the pressure loss in the first tube with a diameter 10 millimeter. First, we need the kinematic viscosity nu. It's given by the dynamic viscosity divided by the density. The value is 1.002, 10 minus 6. We also need the Reynolds number for the friction coefficient. The Reynolds number is 99,000. This means that we have a turbulent flow. The friction coefficient is 0.0178 and the pressure loss is 4,441 Newton per square meter. We will now calculate the flow in the second tube with a diameter 50 millimeters. The Reynolds number is 1996. This means that we are in a transition to turbulence. The pressure loss is 6.4 Newton per square meter, and this is approximately 0. And now we have to calculate the pressure loss due to the shift of the diameter. We need the discharge coefficient, which is 0.9216, and the pressure loss is 45,987.8 Newton per square meter. Now we have our losses all together, then we can calculate the pressure on the inlet. The pressure on the inlet is given by the Bernoulli equation and by the both calculated losses. The pressure on the inlet side will be 608.64 Newton per square meter. In the next line, you find a P1 with an asterisk. The reason is if you use simple foam for calculating the simulation, simple foam uses a specific pressure, means that the pressure is divided by the density of the material. So you will find a specific pressure of 0.09986 square meter divided by square seconds. Now we can make an overview over the three equations. The first picture, this shows the specific pressure out of the Bernoulli equation. This means that we have on the left side a negative pressure. You must understand that the pressures must be seen relatively. Of course, negative pressure is normally not possible, but since we say that the pressure on the outlet is 0, then of course then it's possible to have a negative pressure. But you should consider this more being a pressure difference. In the middle, you find a picture where the loss due to the change in the diameter is considered. So this means that the pressure on the inlet is not minus 50, but it's minus 3.8. In the last picture on the bottom, you see a red line which shows the pressure over the x coordinate. And you see that you start with a pressure of nearly 0.5, which goes down to minus 3.8. And due to the shift in the diameter, the pressure increases up to 0, which is a boundary condition. Now let's go to Freecad, and we will build up the model in Freecad. So first we need a new model. We will start with a part design workbench, and then we go to Sketch and use the sketcher to make a model. Use the XY plane, say OK, and then we can start with a polyline. This model is very easy. We start on the middle axis, go up, go to the right, go again a little up, then go to the right, go to the center line, and then we go back, and everything is fine. We will remove this constraint because this constraint is there are too many constraints, and we must remove this constraint as well. So we get a white line means it's okay, but we need some other constraints. So first we start with this length. We need this constraint. We say this is 50 millimeter. And we want to define the diameter. But in case this is a radius, so this is only 25 millimeter. Okay, and this length is also 50 millimeters. And this diameter is 5 millimeters. Okay, now the sketch has turned to a green line, which means that the sketch is complete. We can go to close, and we want to have a rotation with 360 degrees. We say OK. Okay. The axis, I forgot that, is the x-axis. Now the model is complete, and we can switch to the CfdOF Workbench. We can start with an analysis container. Then we can define the boundary conditions. Here we need an inlet. We go here. We say this is an inlet, and we want to have a uniform velocity with a speed of 10 meter per second. Okay. On the other side, we need an outlet. This one will be the outlet. We define this as outlet, and the subtype is static pressure. Okay. Then in the next step, we need some walls. Okay, this will be the wall, and this will be our wall. and this will be a wall. And we confirm this with OK. So now it's time to build up the mesh. But what you find is that we have here we have a very thin diameter, and here we have a very wide diameter. So in this case, meshing would be a bit complicated because here the mesh should be very fine, and here we can use a mesh with a larger scale. So one possibility to solve this issue is to use the CF mesh. But and for the CF mesh, you can use a different part to define the mesh parameters. I will do so. So I go to the, in this case, I go to the part workbench, and I want to have a cylinder which is covering the first tube. I go to, and now the cylinder is introduced. You find it here, but we have to change the parameters. We want to have a radius of 30 millimeters. The height will be 60 millimeters. And now we have to define the, we have to turn it so it is parallel to the x-axis. So as a turning rotation, we need here the 1, and here is a 0. And we want to have a rotation of 90 degrees. Okay, now it's nearly fine, but the cylinder is not on the position that we wanted to have. So we have to move it in the x direction, going minus 50 millimeters. Oh, that was too much. That was meters. No, now we are fine. Okay. The cylinder is defined. I can say OK. And now we can start to mesh the part. So we start with a revolution. This is our tube model. And we must go back to the CfdOF Workbench. Now we can define the mesh. As I said, I want to have the CF mesh measure. I want to have a base length of 5 millimeters. And okay. I will not write the mesh case because I have to input the mesh refinement. So I can say close. This is the definition of the mesh. If I click on the definition of the mesh, you can see that this button is activated, and you can define a mesh refinement. I will do so. And in this case, I will define it via an internal volume. Internal volume is this one, is a cylinder. I go to add, and I want to have the half of the size. So that means effectively the mesh will be 2.5 millimeters long. I say OK. And I want to have a second refinement. This will be the surface. So I must make this invisible. I make this with the spacebar. I'm clicked on the cylinder. I click on the spacebar, and it disappears. So what I see here is a mesh refinement. I also go on this, click it away. So I can click for the next mesh refinement on this surface. I go to the revolution mesh, go to the mesh refinement, click on this, and say add. And in this area, I want to have also a relative element size of 0.5. In this case, the mesh will not have a base length of 2.5 millimeters, but 1.25 millimeters, because it is double refined. So you have a refinement of the cylinder and you have the refinement of the surface. I say OK. And now I can start the mesh. I click again on the revolution mesh. I say I want to write the mesh case. It's finished. And then I let the mesher run. This running will last about 30 seconds. So see you in 30 seconds. Okay, the meshing is complete. To review the mesh, I click on Load Surface Mesh and I go to Close. And I make the mesh refinement invisible with the spacebar, and I make it invisible, the second mesh refinement, also with the spacebar. Okay, the mesh looks quite fine. We have here a mid-side with a base element size of 2.5 millimeter. Here the size is 5 millimeters. Okay, so we can go to the last steps. We must define a physics model. I make a double click on this. And we want to regard the viscosity. And for the first attempt, I will try to let this run as a laminar flow. In the analytic calculation, we saw that this is a turbulent flow. So normally we should use the Reynolds averaged Navier-Stokes simulation, but I will try this with a laminar. I will show what happens, and yes. Then we must define the fluid properties. I make a double click on it. I want to have water. Here you see the fluid properties. The fluid properties are equal to my analytic calculation. I can confirm this with OK. And then we need an initial value. I click on this. And we can define both as a potential flow. I say OK. And the last step is to save this model. In the last step, we go to the CFD-OF solver, make a double click on it, and write. This means that the case is written. And then we can start the simulation. And now see what happens. The simulation will last about 5 minutes or 10 minutes. So see you in that time. Okay, now the simulation finished, and you will find here the statement simulation finished successfully. When you look on the iterations, you find that the number of iterations is 2000. So when we take a look on the residuum, you see that the residuum was not achieved. The threshold is 10 minus 4. And this was not achieved. What you see is that some kind of vibration or something else occurs. And this might be a sign that there were some problems with the turbulence. Nevertheless, we go to Paraview and take a look on the results. Okay, Paraview has started. We go to the last simulation step. And what we want to see is the pressure distribution over the length. For that, we go to this button. This means plot over line. We click on it. And the starting point here is okay. It's minus 0.5. And the endpoint is 0.05, but these points should be 0. Okay. And I will click here also 0 and 0. So we are looking directly onto the x-axis. And we say apply. And here you see the pressure and the speed. So first take a look on the speed. Okay, that's not what we wanted to see. We take the x component, and you see that the incoming speed is 10, which is okay. The speed here is 0.5, but this is only the speed in the mid-plane. We click this away as well. And here we have our pressure distribution over the x-axis. On the right side we have 0, that's okay. That's what we expected. On the inlet we have minus 0.28. It's in the range that we wanted to have. Now we want to take a look on the flow on the outside. For this, we must apply a slice. We go here to the slice. The direction of the plane is okay, but the position should be on the end. We define this. The origin is 0.049. So now I want to have a look on the speed on the outside, on the outflow. For this, we must apply the slice. Okay, here you see the plane, that's okay. The direction is okay, but it's not on the right position. So we change the position to 0.049, and so now we are on the right position, and I say apply. So now we only see the speed on the outside, which is coming out. We can turn a bit. To see the differences better, we can rescale. Rescale is this button. You find rescale to the data range, and you see that on the midplane, sorry, this is the pressure. We wanted to take a look on the speed. Oh. Okay, you see that in the midplane, we have a high speed, and on the outside, the speed is nearly 0. So what I want to have is some kind of an average value. I go here to the add filter, and I go to data analysis, and I want to integrate. Okay, I say integrate, and I can say apply. And here you see the integrated values. You see the pressure and the speed and so on. Okay, this is an integration over the total area. And if we want to have the mid value, we must divide this by the volume or by the area. I say apply. And then I go to the cell data. And here you find the speed. The speed on the outflow is 0.4. This is what we've calculated in advance. And the pressure is nearly 0. Okay. But you saw that we have some problems with the turbulences. So in the next step, I will use the turbulence model and see what happens. And I close this one. And I close the solver. And I go back to the physics model. I change now to the Reynolds average Navier-Stokes model. And I say OK. Now I can go back to the solver, write the case, and let it run. The convergence is much faster. After 271 iterations, convergence will be achieved. So see you in 1 minute. Okay, now the simulation has finished. Simulation time is 2 minutes. This is a good value. The the residuals is achieved for all parameters. This is good. Let's go to Paraview and take a look on the results. Okay, we go to the last step. Take a look on the speed. Okay, that's kind of interesting, but yes, this model is built up in a way that you can't see inside. Normally, you would build it up with a symmetric constraint, so you can look much easier inside. But in this way, I chose this way. But I can look inside if I make a slice and say that I want it's normal to the y-axis, and then I can say apply. So now I can see a cross section. I should recalculate. So here you see the pressure distribution. This is something coming in, something coming out. That looks good. I can take a look also on the speed distribution. So this is a speed distribution. You see that here we have the boundary condition of 10 meter per second, and here averaged will be 0.4 meter per second. Okay, I delete this slice again. In the next step, I will take a look on the speed distribution over the diameter in the incoming tube. So again, plot over line. And now I must determine where I want to have the line. So I go again to the coordinates. And in this case, I want to have it on the position minus 0.049. And this will also be the second point. And the z coordinate, I will set it to 0. Okay. And here I will start on the lower end. This is minus 0.005. And this is the upper end, 0.05. Okay. Now I'm finished, and I can take a look on the speed distribution. So the parameters for the turbulence, I can put them away. So here you see the distribution. We have here the speed of 10 meter per second, and on the border sides, it's nearly 0. This was our boundary condition. Okay. I can remove this again with delete. And now I want to take a look on the pressure distribution over the x-axis. And again, go to plot over line and go to the starting point. This one minus 0.05 and plus 0.05, that's okay. And the other values, I will set them to 0. Okay. Then I can say apply. And let's take a look. I will remove the parameters again. So only the pressure remains. So what you see is that here we have a higher pressure on the incoming side. It's this specific pressure. This is 5. But what you see is that the loss from this point to this point, it's nearly equal to the analytical model. What has changed is the loss due to the diameter shift. The calculation showed much less losses. And on the right side, we go to 0. So 0 was our boundary condition. And now we can make a comparison of the three simulations, the analytical approach, the laminar approach, and the approach with turbulence. So now here are our results. On the left side, you see the analytical approach. We are weighting a pressure of 0.5 on the inlet. And we expect a pressure loss in the incoming tube of about 5 specific pressure. So let's go on the right side. The top graphic shows a laminar model. We also have some loss inside the incoming model, but this is below the analytical and the model with the turbulence. The picture on the bottom shows the results of the model with the Reynolds average Navier-Stokes equation. So here we have a pressure loss in the incoming tube equal to the analytical model. The pressure loss in the diameter shift is higher than in the analytical model. One reason is, the model I built up on the right side, I only had a length of 50 millimeters. Normally for CFD calculation, this length is too slow, means we have some interaction between the shift diameter and this tube length. Normally it should be much longer. It should be nearly 500 millimeters. I chose this length in order of the calculation time, but what you see is that we get in some way results which are quite near the analytical approach. Okay, let's come to the conclusion. The CFD solution is similar to the analytical approach. The losses in the diameter shift are higher in the CFD model than in the analytical model. Tube losses are nearly equal in analytical solutions and in CFD simulation. And what you must always pay attention is if you take a look on the pressure in simple foam, the pressure is given as a specific pressure with regard to the density rho. Means we have a P asterisk, which is the pressure divided by the density. So now my tutorial number 2 is finished. So thank you very much for your attention, and I hope to see you again in the next tutorial. Bye-bye.